Hi to everyone, myself Dr. Dhananjay Rao, working as assistant professor in the Department of Chemistry. In this session, I am going to cover the topic ultimate analysis of coal. In this session, I am going to cover these topics: ultimate analysis of coal and significance of ultimate analysis. In previous class, I have explained about different types of coal analysis. In that, proximate analysis and ultimate analysis are there. In previous class, I have explained briefly about that proximate analysis. In this session, I am going to cover the ultimate analysis. Proximate analysis is the indirect method. We can measure the quantity of the elements present in the coal by indirect method. But ultimate analysis is the direct method. This is the element analysis and often called qualitative analysis of coal. The ultimate analysis is the qualitative analysis of coal. Analysis involves the determination of carbon and hydrogen, nitrogen, sulfur and oxygen. By this ultimate analysis, we can measure the quantity of hydrogen, nitrogen, sulfur and oxygen present in the coal. See, first analysis of carbon and hydrogen. In this method, first we have to take about 1 to 2 grams accurately weighed coal sample. First we have to take 1 or 2 grams of accurately weighed coal sample and we have to burn this coal sample in presence of oxygen. Means that we have to take first 1 or 2 grams of charcoal. Okay, then we have to burn in presence of oxygen. That the elements present in the coal undergo combustion reactions. The elements present in the coal sample undergo combustion in presence of oxygen. If you burn, that will undergo combustion reactions. See, carbon and hydrogen of the coal are converted into carbon dioxide and water. See, carbon reacts with oxygen. Okay, in presence of oxygen we are burning. So if charcoal contain carbon, okay, this carbon reacts with oxygen, it forms carbon dioxide. Okay, carbon reacts with oxygen, it forms carbon dioxide. This is the combustion reaction. Similarly, if the hydrogen present in the coal, the hydrogen reacts with water, H2 plus O2 give H2O. Okay, the elements present in the coal, carbon or hydrogen reacts with oxygen. If you burn those in presence of oxygen, carbon reacts with oxygen, it undergo combustion reaction, forms CO2. Similarly, hydrogen reacts with oxygen, form water molecules. The gases products of combustion are observed respectively in KOH and CaCl2 tubes, known weights. Okay, for that, after formation of carbon dioxide and water. Okay, after formation of carbon dioxide and water molecules, we have to send this carbon dioxide, the released carbon dioxide gas, we have to send into the known weight KOH tube, known weight of KOH tube, potassium hydroxide tube. Okay, first carbon reacts with oxygen. Carbon reacts with oxygen, forms carbon dioxide. The evolved carbon dioxide gas we have to send into the known weight of the KOH tube. Okay, known weight of the KOH tube. Here, what happens? See, the KOH, the potassium hydroxide, known weight of potassium hydroxide reacts with the evolved carbon dioxide gas. It produces K2CO3, potassium carbonate, and releases water molecules. See, in first step, we have to burn the coal in presence of oxygen. That reaction is combustion reactions. Carbon reacts with oxygen, undergo combustion reaction, it forms carbon dioxide. The evolved carbon dioxide gas we have to send into the known weight of KOH tube or potassium hydroxide tube. The potassium hydroxide tube contain known weight. We have to weigh before the sending the carbon dioxide gas into the KOH tube. Then, after sending the carbon dioxide into the KOH test tube, then the KOH reacts with carbon dioxide. It produces K2CO3, potassium carbonate, and water molecules. Okay, water molecules. Next step, the hydrogen reacts with oxygen, form water molecule. The hydrogen reacts with oxygen, it forms water molecule. This water molecule are sending into the calcium chloride test tube. It contains known weight. So we have to send these water molecules into the known weight of calcium chloride tube. Okay, what happens if this water released in this combustion reaction? Hydrogen reacts with oxygen, form water molecules. This water molecule we have to send into the known weight of calcium chloride tubes. See, the calcium chloride and 7H2O undergo hydration, forms calcium chloride 7H2O. Calcium chloride 7H2O. Okay, in first what happens? We have to the carbon and hydrogen present in the charcoal reacts with oxygen. It forms carbon dioxide. This evolved carbon dioxide we are to send into the known weight of KOH tube. In the KOH tube, KOH present. The KOH reacts with carbon dioxide. It forms K2CO3 and water molecules. Okay. Next step, the released water molecules, H2O molecules, H2 reacts with oxygen. It forms H2O water molecules. These water molecules we have to send into the known weight of calcium chloride tube. Known weight of calcium chloride tube. This calcium chloride reacts with water molecules, forms calcium chloride 7H2O. Calcium chloride 7H2O. Okay. See, if 12 moles of carbon reacts with 12 grams of carbon reacts with oxygen, forms 44 grams of carbon dioxide. 12 grams of carbon reacts with oxygen, it forms 44 grams of carbon dioxide. Similarly, 2 grams of hydrogen forms 18 grams of water molecules. 2 grams of hydrogen molecules reacts with 18 grams of water molecules. See, this is the formula for the percentage of carbon. See, the formula is increase in weight of KOH tube. Increase in weight of KOH tube divided by weight of coal sample taken. Weight of coal sample taken into 12 into 44 into 100. See, why in KOH weight of why KOH tube weight increase? Because of the CO2 absorbed by the KOH. It forms K2CO3. So there is you have to take increase in weight of the KOH tube and divided by the weight of the coal sample taken. The initial weight of the coal sample we have to take. Okay. This is 12. 12 nothing but weight of the carbon. 12 nothing but in the reaction we have to see the 12 grams of carbon reacts with oxygen, forms 44 grams of carbon dioxide. 44 grams of carbon dioxide. See, this 12 nothing but the carbon weight. The carbon weight is 12 grams. The 44 nothing but the weight of the carbon dioxide. The 44 nothing but the weight of the carbon dioxide. This is the 100 for percentage. We have to multiply with 100. Then the formula for the percentage of carbon equal to increase in weight of KOH tube divided by the weight of coal sample taken. Weight of coal sample taken into 12 nothing but weight of carbon divided by 44 nothing but weight of carbon dioxide into 100. For percentage we have to multiply with 100. This is the formula for the percentage of carbon in ultimate analysis. The next formula is percentage of hydrogen. How you can get percentage of hydrogen? See, increase in weight of calcium chloride tube. The released water we have to send into the calcium chloride tube. Hence the calcium chloride weight is increases. So the formula for percentage of hydrogen equal to increase in weight of calcium chloride tube divided by weight of coal sample taken into 2 nothing but hydrogen weight, that is 2 grams. The hydrogen weight is 2 grams. It forms 8 grams of water. Okay, the weight is water weight is 18. The hydrogen weight is 2. The into 100 nothing but to get percent of hydrogen you have to multiply with 100. The formula for percentage of hydrogen equal to increase in weight of calcium chloride tube divided by weight of coal sample taken. Into 2 nothing but weight of hydrogen, 18 nothing but weight of water into 100. This is the percentage of carbon and percentage of hydrogen we can calculate by using ultimate analysis. The next step, then we have to calculate the percentage of nitrogen present in the coal sample by ultimate analysis. See, about 1 gram of accurately weighed powdered coal is heated with concentrated H2SO4 along with K2SO4 in a long necked Geldas flask. For nitrogen estimation, we have to take Geldas, a long necked Geldas flask we have to take. For nitrogen estimation, we have to take long necked Geldas flask. In that, about 1 gram of accurately weighed powder. Okay, for accurate 1 gram of charcoal powder we have to take, and we have to heat this charcoal powder in presence of concentrated H2SO4. Then we have to heat with the concentrated H2SO4. Along with K2SO4 catalyst, we have to add K2SO4 catalyst in this nitrogen estimation long necked Geldar's flask method. First, we have to take long necked Geldar's flask. In that, we have to add 1 gram of charcoal powder, and we have to heat with concentrated H2SO4. To that, we have to add catalyst K2SO4. Okay, we will get in this process, we will get clear solution of coal. Clear solution of coal we will get in this method. First, we have to take 1 gram of coal sample. We have to heat that into we have to heat that coal sample with the concentrated H2SO4 in presence of K2SO4. We will get the clear solution. After the solution becomes clear, it is treated with excess of KOH and the liberated ammonia is distilled over the absorbed in known as the volume of standard acid solution. Okay. After the clear solution you get, okay, then we have to add excess of KOH. For this clear solution, we will get in first step, we will get the clear solution. After this, we have to add excess amount of potassium hydroxide. Solution. See, the clear solution, this reacts with potassium hydroxide, it forms ammonia gas. Okay, it forms ammonia gas. Then we have to send this ammonia gas into the known standard volume of known concentration of H2SO4 at known concentration of acid. Okay, see what happens. See, the sample means coal sample heated with H2SO4 in presence of catalyst K2SO4 potassium sulfate. It forms clear solution. In first step, it forms clear solution. Okay, then we have to treat with excess of KOH. The clear solution obtained is heated with KOH, potassium hydroxide solution. Then it forms ammonia. Ammonia is a gas. Then this evolved ammonia is treated with standard known volume of acid. Means we know the concentration of this acid and volume of the acid we know. Okay, that acid we have to add to this ammonia solution. For that we have to add known standard volume of acid to this ammonia gas. See, NH3. Ammonia contain lone pair of nitrogen contain lone pair of electrons. So it acts as a Lewis base. Donates the electrons. Acid is a Lewis acid. Okay. Then this base and acid reacts together. Okay. The ammonia reacts with this standard known volume of acid. Okay. This is base. This is acid. Acid base reaction takes place. Ammonia and acid reacts together. Okay. Some of the ammonia is taken by the acid. So some of the acid is consumed by the ammonia. The remaining amount of acid is left in that test tube or conical flask. Okay, some of the amount of ammonia is reacts with acid. Okay, the remaining amount of acid is left in that bottle. Okay, then remaining is non-consumed acid. Some of the amount is non-consumed acid. Some of the amount of acid is reacts with the ammonia base. Okay, then for this non-consumed acid, we got non-consumed acid. This non-consumed acid is titrated against with base. That we have to do back titration. Here some of the acid is reacts with the ammonia gas and some of the non-consumed acid is left. Okay, the non-consumed acid is titrated with the base solution. We have to perform back titration. Then we know by this back titration we can know the concentration of the non-consumed acid. By the back titration we will get the non-consumed acid concentration. Okay, na? From that we can know the consumed acid concentration also we can measure. Okay, na? The total concentration in this back titration we will get the non-consumed acid concentration. Okay, na? From the total acid concentration equal to non-consumed acid concentration plus consumed acid concentration. By subtracting the non-consumed acid from the total concentration of the acid, we will get the concentration of the consumed acid. By this method, we can measure the concentration of the consumed acid. From that, From that we can calculate the percentage of nitrogen. From that we can calculate the percentage of nitrogen. See, then volume of acid. Okay, volume of acid we have calculated in the back titration. Okay, the volume of consumed acid and the normality of acid. How much the standard solution we have taken. How much standard solution we have added. Okay, now already we have taken the acid in this. The standard means known concentration of acid. That concentration we have to mention here into 1.4 into 1.4 and divided by weight of the coal sample taken. Divided by the weight of the coal sample taken. Okay, this is the formula for the percentage of nitrogen. In this step, what we have to do? First, we have to take the coal sample, 1 gram of coal sample. For that, we have to add H2SO4 and catalyst K2SO4. Then we will get the clear solution. To that clear solution, we have to add the KOH, excess amount of potassium hydroxide, and heat that solution. It forms the ammonia gas. The ammonia gas is treated with the acid. Okay, na? The standard and known volume of the acid means the concentration of this acid we know and the volume, how much volume we have added also we know. Okay, na? We have to treat it with ammonia with the known volume, standard and known volume of the acid. This ammonia is a base. This ammonia is a base. This ammonia reacts with some amount of the acid. Okay, na? It forms neutralization. Okay, then the remaining acid is there. That is called non-consumed acid. This non-consumed acid titrated against the base. Okay, na? Titrated against the base. We have to perform back titration. Then we know the concentration of the non-consumed acid and the volume of the non-consumed acid. From that non-consumed acid, we can calculate the consumed acid can be measured. Volume of the consumed acid can be also measured. Okay, na? This is the formula for the percentage of nitrogen. From this volume of acid, how much the volume consumed, we can know by this back titration method, and into normality of the acid, how much normality you have taken in the initially, that you have to mention here, into 1.4 divided by weight of the coal sample taken. How much sample you have taken initially, you have to mention here. By that we can calculate the percentage of nitrogen. Then next step we have to calculate the percentage of sulfur present in the coal by using ultimate analysis. The known weight of coal combusted in a bomb kilometer, presence of barium chloride. The known weight of coal sample you have to take, then we have to burn in presence of bomb kilometer. In the bomb kilometer, we have to burn this coal solution. Okay, now in presence of barium chloride. In presence of barium chloride. If any sulfur present in sample, if coal sample contain any sulfur molecules, okay, na, that will be converted into barium sulfate. Barium chloride reacts with this sulfur. Okay, it forms barium sulfate. First, sulfur reacts with oxygen, forms sulfate ions. Sulfur reacts with oxygen, it forms sulfate ions. These sulfate ions reacts with barium chloride. These sulfate ions reacts with barium chloride. It forms barium sulfate. It forms barium sulfate. Then we can calculate the percentage of sulfur. Then by using the formula, percentage of sulfur equal to weight of barium sulfate obtained. So we have to measure the weight of this barium sulfate. Barium sulfate is a precipitate. Okay, we have to measure the barium sulfate weight of the barium sulfate obtained divided by the weight of the coal sample taken in a bomb. Weight of the coal sample taken in a bomb into 32 divided by 233. 32 nothing but weight of the sulfur. Weight of the sulfur. 233 nothing but the weight of the barium sulfate. 233 grams nothing but weight of the sulfate. Into 100 nothing but we have to multiply for the percentage of the sulfur. The formula for the percent of sulfur equal to weight of the barium sulfate obtained divided by the weight of coal sample taken in bomb into 32. 32 nothing but weight of the sulfur and 233. 233 nothing but weight of the barium sulfate into 100. Percentage of ash. See, but ultimate analysis of coal percentage of carbon, hydrogen, nitrogen, sulfur, ash, oxygen in the coal can be calculated. Okay, na? By ultimate analysis we can calculate all those things. Percentage of ash. Ash determination is carried out in proximate analysis. Okay, na? Ash percentage we can't calculate by using ultimate analysis. For percentage of ash we have to calculate from the proximate analysis. In the previous class I have explained how to calculate the percentage of ash. The percentage of ash formula from proximate analysis is weight of ash left into 100 divided by the weight of coal sample taken. Weight of the ash left into 100 divided by the weight of coal sample taken. This percentage of ash obtained from the proximate analysis. Then percentage of oxygen. How you can calculate the percentage of oxygen? See, the formula for the percentage of oxygen equal to 100 minus percentage of carbon. Already we calculated percentage of carbon, and percentage of hydrogen also we have calculated. Percentage of sulfur we have calculated. Percentage of nitrogen by Geldar's method also we have to calculate, and percentage of ash. If you subtract all these percentages from the 100, if you subtract all these percentages, carbon, hydrogen, sulfur and nitrogen and ash, if you subtract all these percentages from the 100, then we will get the percentage of oxygen. The percentage of oxygen formula equal to 100 minus percentage of carbon plus hydrogen plus sulfur plus nitrogen plus ash. Okay, we will get the percentage of oxygen. See, these are the formulas obtained from the proximate and ultimate analysis. This is the formula for the ultimate analysis. By percentage of carbon equal to increase in weight of KOH test tube, increase in weight of KOH tube divided by the weight of coal sample taken, into 12 divided by 44 into 100. Here 12 nothing but weight of the carbon, 44 nothing but weight of the carbon dioxide. This is the percentage of carbon in ultimate analysis. The next formula is percentage of hydrogen. Here the increase in weight of calcium chloride tube divided by weight of coal sample taken into 2 divided by 18. 2 nothing but weight of the hydrogen, 18 nothing but weight of the water molecule. Okay. Then percentage of nitrogen. The formula for the percentage of nitrogen. Here volume of acid into normality of the acid into 1.4 divided by the weight of the coal sample taken. See, the 1.4 obtained from the 14. Okay, actually the volume we obtained in the ml. So we have to convert into concentration terms in liter terms. Okay, that's why 14 nothing but 14 the weight of the nitrogen gas, and divided by this with 100,000. We have to convert into liter. Okay, na? We will obtain in ml. We have to convert it into liters into 100. For the concentration, we have to multiply with 100. Then this get cancelled. Then remaining is 1.4. That's why I am writing here 1.4. See, the percentage of nitrogen equal to volume of acid into normality of acid into 1.4 divided by the weight of coal sample taken. Then percentage of sulfur. The percent of sulfur nothing but weight of barium sulfate obtained. Divided by the weight of coal sample taken in bomb. Into 32. 32 nothing but weight of the sulfur, and 233 nothing but the weight of the barium sulfate into 100. These are the formulas obtained from the ultimate analysis. See, the significance of ultimate analysis. What is the significance of the ultimate analysis? In that, the significance of carbon and hydrogen. The greater the percentage of carbon and hydrogen, better is the coal in quality and calorific value. If the coal contain high percentage of carbon and hydrogen, okay na, it is a good quality of coal. Okay na, it gives the highest calorific value on burning. On burning, the carbon if coal contain more high percentage of carbon and hydrogen, it produces large amount of calorific value on burning. Nitrogen, okay na, the percentage of nitrogen. Nitrogen has no calorific value, and hence its presence in coal is undesirable. The nitrogen has no calorific value. No, on burning it will not produce calorific value. So if the nitrogen has no calorific value. So in presence, okay, its presence, nitrogen presence, the coal is undesirable. The nitrogen presence is undesirable in the coal sample. Thus, a good quality coal should have very little nitrogen content. A good quality coal should contain very little amount of nitrogen. If little amount of nitrogen contain, that coal is good coal. The good quality coal should not contain more percentage of nitrogen. It should contain less number of nitrogen. Less percentage of nitrogen. The significance of sulfur. The sulfur, although contributes to the heating value of coal, it on combustion produces acids like sulfur dioxide, sulfur trioxide, which have harmful effect of corroding the equipments. Okay na? Sulfur, if coal contains sulfur, on sulfur burning it produces sulfur dioxide and sulfur trioxide gases. These are the harmful for the corroding equipment. These corrode the equipments, and also it is also harmful for the atmospheric pollution. It causes the atmospheric pollutions. The sulfur dioxide and sulfur trioxide release when the sulfur present in the coal. If you burn the coal, the sulfur reacts with oxygen, forms sulfur dioxide and sulfur trioxide. These sulfur dioxide and sulfur trioxide, these are the environmental not friendly gases. Okay na, greenhouse gases. Okay na, these causes atmospheric pollutions, and also these gases corroding the equipment. These corrode the equipment. Okay. Presence of sulfur is highly undesirable in coal to be used for making coke for iron industry. If the presence of sulfur is highly undesirable in coal, okay, the coal should not contain the sulfur. Okay, na? If sulfur present, okay, na, it is difficult to making coke for iron industry. We can't use this type of coal in the iron industry, since it is transferred to the iron metal and badly affect the quality and properties of the steel. The sulfur reacts with the steel and quality of the iron. This reduce the quality of the steel and iron. Moreover, oxides of sulfur pollute the atmospheric, leads to the corrosion. Okay, na? These oxides, the sulfur dioxide, sulfur trioxide, sulfur oxides are corrode the equipment, and also cause the atmospheric pollutions. Ash. Ash is useless. Ash is useless, and this is non-combustible matter. Ash is a non-combustible matter which reduces the calorific value of coal. It reduces the calorific value of coal. Moreover, ash causes the hindrance to the flow of air. Ash causes the hindrance to the flow of air and heat, thereby lowering the temperature. That's why thereby lowering the temperature. Hence, lower the ash content, better the quality of coal. If the coal content low amount of ash, that is quality coal. That is called quality coal. The presence of ash also increases. Transporting, handling, and storage costs also increases. The presence of ash increases. If the ash percentage increases, the transporting and handling and storage cost also increases. The presence of ash also causes early wear of furnace walls, burning of apparatus. The presence of ash also causes the early wear of furnace walls. Okay, burning of apparatus. The significance of oxygen. The oxygen content decrease the calorific value of coal. Oxygen, if the oxygen present, that decrease the calorific value of coal. Oxygen is combined from the hydrogen. The hydrogen and the hydrogen present in the coal reacts together from water molecules. The hydrogen available for the combustion is lesser than the actual one. Actually, the hydrogen present, the hydrogen is percentage more, that will give the highest calorific value. In the first point we have discussed, if the hydrogen and carbon percentage more, it releases highest calorific value. If oxygen present in the coal, that oxygen reacts with the hydrogen present in the coal. Okay, na? Means that oxygen reduce the percentage of hydrogen present in the coal. That's why the calorific value decreases. An increase in 1% of oxygen. An increase in 1% of oxygen, it decreases the calorific value by 1.7%. 1% oxygen present, that decrease the 1.7% of the calorific value. So, oxygen is undesirable in the coal sample. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.